NASA expected Titan to be cold, distant, and inert. Instead, in January 2005, the Cassini-Huygens mission revealed something no one anticipated: a functioning world. For decades, Saturn's largest moon appeared as a smooth orange sphere through telescopes. Its dense nitrogen atmosphere blocked visible light, hiding the surface completely. Scientists could measure its size, approximately 5,150 kilometers in diameter, and calculate its orbit far from the Sun. Surface conditions, however, remained speculative. Some models proposed a frozen crust. Others suggested a global hydrocarbon ocean. None could be confirmed. The central question was simple but consequential. Was Titan geologically dead, or was it active? The presence of methane in its atmosphere created a scientific dilemma. Methane is chemically unstable under solar radiation. Over tens of millions of years it should break apart, yet it persisted. That persistence implied replenishment, and replenishment implied active processes occurring either at the surface or below it. On January 14, 2005, under the authority of NASA and the European Space Agency, the Huygens probe descended through Titan's atmosphere. It transmitted images during a 2-hour fall before landing on the surface. What NASA found changed planetary science. They found river channels branching across the landscape. They found rounded pebbles shaped by erosion. They found evidence that liquid had flowed across Titan's surface. Further observations from the Cassini orbiter confirmed vast seas of liquid methane and ethane near the poles. Not frozen reservoirs, not temporary frost, stable bodies of liquid. Titan became the only other known world in the solar system with persistent surface liquids. This discovery redefined the stakes. If Earth was no longer unique in hosting active surface cycles, then habitability could not be restricted to warm, water-based environments alone. NASA had not found life, but they had found a moon that behaves like a planet. NASA had not found life, but they had found a moon with rivers, seas, weather, and chemistry in motion, a world operating under physical laws, familiar in structure, yet alien in substance. And if such a system can exist in the deep cold beyond Saturn, then the question is no longer whether Titan is extraordinary. The question is how many other worlds like it are waiting, still hidden behind their own veils. On January 14, 2005, humanity fell through an alien sky. At 10:13 UTC, the European Space Agency's Huygens probe entered Titan's upper atmosphere at more than 20,000 kilometers per hour. Designed in collaboration with NASA as part of the Cassini-Huygens mission, it carried cameras, spectrometers, and atmospheric sensors. Its objective was clear: penetrate the haze and determine what truly existed at the surface. No probe had ever landed in the outer solar system. The stakes were significant. If Titan's surface proved inert, decades of speculation about active chemistry would collapse. If liquids were confirmed, planetary science would expand into new territory. As Huygens descended, friction slowed its fall. Parachutes deployed in sequence. Instruments began transmitting data across nearly 1.4 billion kilometers back to Earth. The first breakthrough came before landing. Through gaps in the haze, the descent imager captured branching, dark patterns etched across brighter terrain. They resembled river drainage networks seen from orbit around Earth. Their geometry was unmistakable. Channels converged, split, and curved with natural precision. These were not fractures in ice. They were carved features. At an altitude of roughly 8 kilometers, additional images revealed elevated highlands cut by valleys. The evidence suggested erosion by flowing liquid. When Huygens touched down, the final confirmation arrived. The surface was not smooth ice. It was scattered with rounded pebbles, each several centimeters across. Their edges were worn, their contours softened. On Earth, such shapes form when stones are transported and tumbled in moving water. Here, at minus 180 degrees Celsius, the same process had occurred. Only the liquid was methane or ethane. The probe operated for just over an hour on the surface before its batteries failed. But in that brief window, Titan transformed from abstraction into terrain. NASA and ESA had confirmed active surface processes on a moon once considered frozen and static. Liquid had flowed. Landscapes had evolved. Titan possessed geology in motion, yet Huygens had landed at only one location. A single site could not reveal the full scale of Titan's system. The true extent of rivers, lakes, and climate cycles remained uncertain. To understand whether this was a localized phenomenon or a global network, scientists would have to look from above. And orbiting high overhead, Cassini was already preparing to see what Huygens could not. From orbit, the mystery deepened. After the Huygens landing in January 2005 confirmed localized evidence of erosion, NASA's Cassini spacecraft began a systematic campaign to map Titan from above. Visible cameras remained nearly useless. The moon's thick atmospheric haze scattered light and concealed the terrain. To overcome this barrier, scientists relied on Cassini's synthetic aperture radar instrument, capable of penetrating the smog and resolving surface features through reflected radio waves. What emerged from those radar passes challenged every conservative model. Beginning in 2006, repeated flybys revealed vast, dark regions clustered near Titan's polar areas. In radar imagery, these regions appeared smooth and uniform, absorbing signals in a manner consistent with liquid surfaces rather than solid ice. Yet radar reflectivity alone was not sufficient proof. A flat, icy plain could mimic similar signatures. The stakes demanded confirmation. That confirmation arrived in July 2009. During a carefully planned observation sequence, Cassini's imaging system captured a specular reflection from Titan's northern hemisphere. Sunlight glinted off the surface of what would later be identified as Kraken Mare. The reflection behaved precisely as light does when it strikes a liquid body at the correct angle. The geometry was consistent. The brightness profile matched theoretical predictions. This was not inference, it was direct optical evidence. Subsequent radar altimetry measured depths exceeding 100 meters in portions of Kraken Mare. Other seas, including Ligeia Mare and Punga Mare, displayed similar characteristics. The scale was extraordinary. Kraken Mare alone covers an area larger than all of North America's Great Lakes combined. For the first time in planetary exploration, a world beyond Earth was confirmed to host stable surface seas. The implications extended beyond geography. If Titan maintained large reservoirs of liquid methane and ethane, then it required a replenishing cycle. Evaporation, condensation, precipitation, a climate system operating at minus 180 degrees Celsius. Cassini's radar maps began revealing branching channels feeding into these polar basins. The pattern was unmistakable. Titan was not merely storing liquid, it was circulating it. A hydrological system existed, built not on water but on hydrocarbons, yet seas and rivers alone do not define a climate. To understand whether Titan truly possessed a functioning atmospheric engine, scientists needed to examine the sky itself. And what they would discover above the surface proved just as extraordinary as the oceans below. A moon should not have weather like this, yet data returned by NASA's Cassini spacecraft between 2005 and 2017 revealed that Titan's atmosphere is not a static shell of gas, but a dynamic engine. Measurements confirmed surface pressure nearly 1.5 times that of Earth at sea level. For a satellite orbiting 1.4 billion kilometers from the Sun, such atmospheric density is extraordinary. The central discovery was not simply thickness, it was motion. Using Doppler tracking and atmospheric modeling, scientists determined that Titan's upper atmosphere rotates far faster than the surface below it. While Titan completes one rotation every 16 Earth days, winds at high altitude can circle the Moon in roughly a single Earth day. Wind speeds reach up to 200 meters per second. This phenomenon, known as superrotation, was previously observed on Venus, but its presence on Titan forced a reassessment of atmospheric physics under cryogenic conditions. Solar energy at Saturn's distance is weak, yet it is sufficient to drive circulation cells, seasonal cloud formation, and global transport of methane. Cassini observed cloud systems shifting hemispheres as Titan moved through Saturn's long seasonal cycle. Infrared instruments detected storm activity concentrated near polar regions, consistent with methane condensation and rainfall. These findings confirm that Titan's seas are sustained by atmospheric exchange rather than isolated reservoirs. The stakes extended beyond meteorology. Methane in Titan's atmosphere should be destroyed by ultraviolet radiation over tens of millions of years. Its continued presence implies active replenishment, possibly from subsurface sources. A balance must exist between destruction and renewal. Titan's climate is therefore not temporary, it is maintained. In 2022, the James Webb Space Telescope strengthened this conclusion by detecting methyl radical, a highly reactive intermediate molecule in Titan's upper atmosphere. Its presence demonstrated that complex chemical reactions are occurring continuously, reshaping atmospheric composition in real time. This is not a dormant moon wrapped in haze. It is a world where chemistry circulates through sky, rain, river, and sea, forming a planetary-scale cycle built on hydrocarbons instead of water. But circulation alone does not answer the deeper question. If Titan's atmosphere manufactures complex organic molecules and deposits them across the surface, what happens next when those compounds accumulate, interact, and organize over time? To understand that possibility, the focus must shift from weather to chemistry. The most important discovery on Titan cannot be seen with the naked eye. Between 2005 and 2017, NASA's Cassini spacecraft found that Titan's thick atmosphere is constantly creating complex organic molecules. High above the surface, sunlight breaks apart methane and nitrogen gas. The broken pieces then recombine into heavier carbon-based compounds. Over time, these molecules grow larger and slowly fall down through the orange haze like fine dust. This was not a small or rare process. It was continuous. Cassini's instruments detected many different types of organic molecules in the upper atmosphere. Some were surprisingly large and complicated. When scientists recreated Titan's conditions in laboratories on Earth, they confirmed that similar reactions can produce solid organic material. Over billions of years, this process may have covered Titan's surface with carbon-rich deposits. Why does this matter? On Earth, before life began, there was chemistry. Simple molecules combined, reacted, and slowly formed more complex structures. Titan shows us a world where rich organic chemistry is happening naturally, even in extreme cold. However, Titan's surface temperature is around -180 degrees Celsius. At such low temperatures, chemical reactions happen very slowly. Life as we know it depends on liquid water and warmer conditions. Titan has neither at the surface. Even so, scientists have proposed an interesting idea. In liquid methane, certain molecules might be able to form tiny bubble-like structures. These structures could separate inside from outside, similar to how cell membranes work on Earth. Compartmentalization is one of the first important steps toward life. So far, no spacecraft has confirmed that such structures exist on Titan, but the necessary ingredients are present: a thick atmosphere producing organic molecules, stable lakes and seas of methane, and billions of years for chemistry to experiment. Titan may not host life, but it clearly hosts active, large-scale organic chemistry. The next step is to move beyond detecting molecules from orbit and begin testing Titan's surface directly. Only then can we understand how far this chemistry has truly progressed. To understand Titan, we must land again. But this time, we will not stay in one place. In 2019, NASA officially selected Dragonfly as part of its New Frontiers program. The mission is scheduled to launch in 2028 and arrive at Titan in the mid-2000s. Unlike any spacecraft sent to another moon, Dragonfly is not a rover and not a stationary lander. It is an 8-rotor aerial vehicle, engineered to fly through Titan's dense atmosphere. The central discovery driving this mission is clear. Titan possesses active organic chemistry and stable surface liquids, but Cassini observed from orbit, and Huygens sampled only a single landing site in 2005. Critical questions remain unanswered. How complex are the organic molecules on the surface? Do different regions contain different chemistries? Has any organization emerged beyond simple reactions? Dragonfly is designed to address these uncertainties directly. Titan's environmental conditions make flight not only possible but efficient. Surface gravity is about 1/7 that of Earth, and the atmosphere is thicker than our own. These factors allow a rotorcraft to lift off with far less energy than would be required on Earth. Each flight will cover kilometers at a time, enabling exploration across multiple geological settings. The primary landing zone will be the Shangri-La dune fields near Titan's equator. From there, Dragonfly will travel to icy plains, ancient impact craters, and possibly regions where subsurface material has been exposed. Onboard mass spectrometers and chemical analyzers will examine surface samples in detail, identifying molecular structures rather than inferring them remotely. The stakes are significant. If Titan's surface chemistry shows increasing levels of complexity, it could suggest that prebiotic processes are more flexible than once believed. If instead the chemistry remains limited, that result will still define the boundary conditions for life in extreme cold. Dragonfly will also measure temperature, wind, and atmospheric composition directly from the surface. These data will refine climate models and test long-standing hypotheses about methane replenishment and seasonal cycles. For the first time, Titan will not be observed in fragments. It will be studied as a connected system, across landscapes separated by kilometers, yet linked by chemistry and climate. When Dragonfly begins transmitting its findings, speculation will give way to evidence, and what that evidence reveals may determine whether Titan is merely chemically rich or something far more consequential. Titan's most important ocean may be hidden. Long before Dragonfly's scheduled arrival in the mid-2030s, data from NASA's Cassini mission began pointing towards something beneath the surface. Between 2005 and 2017, precise measurements of Titan's gravity field and rotational behavior revealed subtle variations that could not be explained by a completely solid interior. The central discovery emerged from tracking Titan's tidal response as it orbited Saturn. Gravitational pull from Saturn slightly flexes the Moon. Cassini's radio science experiments measured this distortion. The magnitude of the flexing suggested that Titan's outer ice shell is decoupled from its core by a global subsurface ocean. Models indicate this ocean is likely composed of liquid water mixed with ammonia, kept from freezing by internal heat and chemical antifreeze effects. At surface temperatures near -180 degrees Celsius, such a reservoir seems improbable. Yet pressure and tidal heating change the physics deep below. The stakes are significant. If Titan possesses a stable internal ocean, it joins a small group of ocean worlds in the outer solar system. Liquid water beneath ice expands the range of potentially habitable environments. Unlike the methane seas on the surface, a water-ammonia ocean would provide a medium more familiar to terrestrial biochemistry. There is no direct sampling yet. The ocean remains inferred through gravitational data and modelling, not visual confirmation. However, the evidence is consistent across independent analyses conducted by mission scientists. An additional question follows. Does material exchange occur between the surface and the interior? Cryovolcanic features have been proposed, though debated. If fractures allow organic compounds from the surface to migrate downward, Titan may host two parallel chemical systems, hydrocarbon chemistry above and water-based chemistry below. Such dual environments on a single world would be extraordinary. Titan would not simply be chemically active, it would be layered in complexity. To determine whether these systems interact, future missions must integrate surface chemistry, geophysics, and atmospheric data into a unified model. And beyond Titan, similar ocean worlds orbit in darkness throughout the outer solar system. Titan is no longer an anomaly, it is a prototype. In the years following Cassini's discoveries between 2005 and 2017, planetary scientists began reassessing data from beyond our solar system. Observations from missions such as Kepler and ground-based spectroscopic surveys revealed that planets and moons with thick atmospheres and volatile, rich compositions are not rare. Sub-Neptune-sized worlds and icy satellites appear common around other stars. The central realization is this: if Titan can sustain stable surface liquids under cryogenic conditions, then Earth-like temperatures are not the only pathway to active planetary systems. Statistical analyses of exoplanet populations indicate that volatile rich bodies may outnumber rocky Earth-sized planets. Many orbit far from their stars, where surface temperatures resemble Titan's rather than Earth's. While direct imaging cannot yet resolve seas or dunes on these distant objects, Atmospheric modelling suggests that methane, nitrogen, and hydrocarbon chemistry could persist under similar energy balances. The stakes extend to one of astronomy's most enduring equations. The Drake equation attempts to estimate the number of communicative civilizations in our galaxy. One of its key parameters is the fraction of planets that develop life. Traditionally, this calculation has focused on the so-called habitable zone, where liquid water can exist at the surface. Titan challenges that boundary condition. If complex chemistry can organize in methane solvents, and if subsurface oceans exist beneath frozen crusts, then habitable environments may be more diverse than once assumed. The definition of habitability expands from a narrow orbital band to a spectrum of chemical possibilities. This does not mean Titan hosts life. No evidence supports that conclusion, but it demonstrates that planetary systems can maintain dynamic cycles, organic synthesis, and potential chemical reservoirs far outside Earth-like climates. In 2022, continued atmospheric analysis using the James Webb Space Telescope reinforced this perspective, detecting reactive intermediates that confirm active chemistry in Titan's upper layers. These findings strengthen the case that similar processes could operate on countless cold worlds across the galaxy. Titan reframes the search. Instead of asking only where water is liquid, scientists must now ask where chemistry persists and evolves over time. And if such chemically active worlds are common, then our solar system may not be unique in hosting them. The next step is to consider what this means for life itself, not only where it might exist, but how many forms it could take. The search for life has always been guided by a single assumption: follow the water. For decades, NASA and the broader scientific community focused on worlds within the classical habitable zone, where liquid water could exist on the surface. Mars, Europa, Enceladus. Each became a target because water is central to life as we understand it. Titan did not initially fit that framework. Its lakes are methane. Its temperature hovers near -180 degrees Celsius. By traditional standards, it should have been excluded. Yet discoveries made between 2005 and 2022 forced a reconsideration. Cassini confirmed stable surface liquids. It detected extensive organic chemistry in the atmosphere. Gravitational delta suggested a subsurface ocean. The James Webb Space Telescope later identified reactive intermediates that demonstrate chemistry unfolding in real time. None of these findings prove biology, but collectively they establish something equally important. Titan satisfies several preconditions once thought unique to warmer worlds. The central discovery is conceptual. Habitability may not depend solely on temperature or water, but on sustained chemical disequilibrium. Titan maintains active cycles, methane evaporates, condenses, and rains. Organic molecules form continuously and accumulate. Energy, though faint from the distant sun, is sufficient to drive atmospheric motion and molecular transformation. The stakes are scientific and philosophical. If life is defined not by its specific ingredients, but by organized chemistry capable of replication and evolution, then Titan represents a test case for alternative pathways. Even if biology has never emerged there, the Moon demonstrates that planetary systems can maintain complexity without Earth-like conditions. Astrobiology is therefore shifting from a narrow search for Earth analogues to a broader investigation of chemical environments. Titan stands at the center of this transition. It compels researchers to refine definitions, develop new instruments, and question long-standing assumptions embedded in planetary science. The coming decades, particularly with Dragonfly's arrival in the mid-2000s and 30s, will determine whether Titan's chemistry remains prebiotic or approaches a deeper threshold of organization. And whatever the answer, it will not apply to Titan alone. It will influence how we interpret every cold world orbiting distant stars. Titan did not give us life, it gave us a new definition of possibility. When the Cassini-Huygens mission arrived in the Saturn system in 2004, Titan was considered an atmospheric curiosity. By the time Cassini concluded its mission in 2017, under NASA's authority, that perception had fundamentally changed. Radar mapping confirmed seas of liquid methane. Atmospheric measurements revealed active weather and super-rotating winds. Spectrometers detected complex organic chemistry unfolding continuously. Gravitational analysis indicated a probable subsurface ocean beneath an icy shell. The central discovery was not a single image or molecule. It was the realization that Titan operates as a complete planetary system. Rain falls, rivers carve channels, dunes migrate under persistent winds, organic particles descend from the sky and accumulate across the landscape. Energy flows, matter cycles, and chemistry persists over geological timescales. All of it occurs at temperatures near minus 180 degrees Celsius, far beyond the traditional habitable zone. The stakes extend beyond this moon. For generations, the search for life relied on a narrow template: liquid water, moderate warmth, and Earth-like conditions. Titan demonstrates that complex, stable systems can arise under radically different circumstances. It expands the framework within which astrobiology operates. Habitability is no longer confined to a thin orbital band around a star. It may include cold worlds with dense atmospheres, active chemistry, and internal oceans. In 2028, NASA will launch Dragonfly to test these conclusions directly, with arrival expected in the mid-2030s. That mission will not search for organisms in the conventional sense. It will measure chemistry, structure, and environmental interactions with precision instruments. The objective is evidence, not speculation. Whether Dragonfly discovers increasingly organized organic systems or confirms that Titan's chemistry remains prebiotic, the outcome will refine our understanding of life's boundaries. Titan has already altered planetary science. It revealed that Earth is not the only world where landscapes evolve, climates circulate, and complex molecules assemble over time. The question is no longer whether Titan is unique. The question is how many other worlds in the galaxy are following similar chemical paths, unseen, waiting beyond the reach of our current instruments.